Hi, everybody. I guess we'll get started. I'm Brandon Berryhill, for those of you that don't know me. If you do know me, I'm also still Brandon Berryhill. So originally this introduction was supposed to be given by Bruce Levin. In fact, Bruce wrote about 10 paragraphs worth of introduction. He was able to write so much because Marc was here in the 1990s, mid-1990s, before I was deployed. Me, as professor of epidemiology at Harvard Chan School of Public Health and his service as director of the Center for Communicable Diseases, Bruce, on the other hand, was able to extol Marc's virtues and included among his praise a quote from the Talmud, which states, "We learn a lot from our teachers, we learn more from our colleagues, but we learn most from our students," of which he pointed to Marc as the shining example. I could never be so eloquent. Bruce went on to explain how while in the lab, Marc joined in on several projects, such as modeling the control of hospital-acquired infections and antibiotic treatment, as well as having his own independent, sans Bruce, projects on pneumococcus and the vaccines employed to treat pneumonia. Many of you may know Marc from his research on the coronaviruses, particularly on the COVID-19 pandemic. In addition to doing some fundamental research on the epidemiology of pharmacological and non-pharmacological interventions, he has also played and continues to play a major role in science communication. So with that in mind, please welcome to the stage Marc Lipsitch to communicate about how everything keeps changing and the lessons of COVID-19 for surveillance, epidemiology, and modeling.
Thank you, Brandon, and thank you for keeping it short. I can only imagine the libel and slander there would have been if Bruce had given it. And in the interest of short and in the interest of starting with a joke to honor my distinguished mentor, Bruce Levin, I will say that it's exciting to be here again in the new millennium. It's not that new anymore. And that it's great that you guys have a program in infectious diseases across scales, because when I was here, it was just Bruce Levin and Weston Antia, and they're both really short, but now that we have a Dutch person involved, we have a two scale. That's real diversity. Thank you for laughing. Our payment will be distributed after, but I've been thinking about that joke the whole day. So, yes, in many ways. But it's fun to see old friends and meet some new ones today. And it's fun to be back. Something I think this building didn't exist. So everything keeps changing really is kind of what it felt like throughout the effort to make sense of the facts in COVID-19. And I want to talk a little bit about some perspective on how to do surveillance and epidemiology in those circumstances. I want to make the argument that surveillance and epidemiology should blur when facts are changing, because epidemiology is supposed to find generalizable truths about the world, but if they're only generalizable for 2 weeks, and then something's going to change, you probably need to redo the study. And so many types of questions that we thought of in research become questions for surveillance. And then the second half, as time allows, I want to talk about some work that we recently done to try to get more precise about how epidemiologic and surveillance studies can be carefully designed and interpreted to provide the inputs for mathematical models. I'll get to that. So, let's see. So you teach about surveillance or ask people about surveillance. Lots of people know what it is, and if you ask 6 people what it is, they'll each give you a different answer with great confidence. And they're all right. There are lots of things that we mean by surveillance, and I want to describe some of the common ideas about it and then relate it to the situation with COVID. One of the most interesting documents on surveillance that I've ever read is this WHO report on the ethics of public health surveillance, which I thought when I read it was going to be about why you shouldn't violate people's privacy and why surveillance could be dangerous and all that sort of thing. And it mentions that, but it basically says something that actually a community group that we talked to recently about a project with private design on surveillance, articulated very clearly, which is that people who don't get counted don't get services. And part of being underrepresented is being undercounted. And so the WHO points out that if you don't do surveillance in a particular area or in a particular group, you don't know what is needed to deal with the health of the population, and you therefore don't deal with it. And so it almost doesn't quite go to the extent of defining a human right to be under public health surveillance, but it sort of moves in that direction. People who are on the data side focus on a completely different set of issues, which is the data accessible? Is the machinery of the surveillance system well designed to get the data from the point of origin to the user and to the reuser? And that's also a very important aspect. And a third view of surveillance that is common among people who work in laboratories is that what we want to do with surveillance in public health is to find unusual things, to detect the new threat, to enrich for the most unusual and interesting things, so that you can see those things when they're still rare. And that's also sometimes really important, and sometimes quite destructive to the thing you're trying to do. Back right after the 2009 flu pandemic, a large group of colleagues had a meeting, and then we wrote a paper that's this one cited at the bottom there. And then we redrew the figure with help from graphic artists, because PowerPoint is not actually a drawing software, it turns out. And it actually helps to have someone who can do it better. So we employed someone who's competent to make a nicer figure, to try to make the point that what I think is a good overall view of surveillance for public health is that in a pandemic, for example, you have a set of decisions you want to make. Those are listed across the top in small print, I'm sorry, but they're things like the overall scale of the response, choosing which countermeasures to use for direct protection and for indirect protection, for reducing transmission, how to balance between those two, when to scale down the response, and so forth. You know, a bunch of those kinds of decisions. To make those decisions well, you need evidence about things like how contagious the virus is, how severe it is per case, who gets severe infections and who doesn't, how well control measures work, and so forth. And the inputs to that are surveillance inputs. Those are things like surveillance of viruses, data from hospitals, surveys of people, serologic data, and case reports, and so forth. And you integrate, you ask a question up here, you figure out your evidence needs, and you then figure out what surveillance inputs you need, and you integrate out the machine. That's a really beautiful picture, in my opinion. I love all the colors. It doesn't happen in real life. That is not how surveillance is typically designed. But I think it is how surveillance systems should be designed. They should be designed with specific decisions that they're meant to support in mind. And that's going to be kind of a theme of what we had for COVID, particularly in the United States, was a system that didn't actually measure any quantity that epidemiologists have a name for. It measured cases of positive tests, numbers of people hospitalized, but most directly the number of positive tests on a day in a given geographic area. And the inputs into that system were things that we all have names for as epidemiologists, like incidence and duration, which gives you prevalence. But then it gets filtered through all these things that vary in space and time and don't necessarily get well quantified, like why people get tested, why they can't get tested, why they don't want to get tested, how well the test works, and whether the test gets reported. And through that big funnel, you eventually get this reported case number, which was one of the major ways that we did surveillance in the United States, and quite unhelpful in many cases because it varied so much in space and time. The reasons why people wanted to get tested varied, the availability of tests varied, the politics of the area and whether they wanted to put money into doing testing varied, and so forth. So in thinking about sort of what we learned from COVID, I I want to propose that we try to define a relatively small number of things that we want to do with surveillance. And then rather than trying to build one system that does all of them, try to build purpose-built tools which we can call together a surveillance system for which each are designed to do a specific thing. 4 of the things that we want to do with surveillance, I'll argue, are detecting new things, new variants or the virus in the first place, assessing individuals for their treatment, characterizing severity and whether the countermeasures work or not, like vaccines and monoclonal antibodies, and defining the burden. And some of those things probably sound like surveillance to everyone, like detection. Some of them probably don't sound like surveillance, like characterizing severity. And I'll try to make an argument for why I'm putting them all together in a few minutes. But I want to spend a little bit of time thinking about why we want to do each of these kinds of surveillance, or at least I'm not going to go through all 4, but a couple of them as examples. So why do we want to detect things? I think that's pretty obvious. We want to be able to detect things so that we can start responding to them. The group of 7 industrialized countries and more recently CEPI, the Coalition for Epidemic Preparedness Innovations, have defined this 100-day mission that within 100 days after finding a new virus or a new potential pandemic threat, we should have countermeasures ready. That's an incredibly ambitious thing, but the value of doing that is much greater if we find it early than if we find it late. In COVID, we saw that we needed to prepare for the spread of new variants. We saw the Omicron variant rising in Southern Africa and knew that there was a risk to our healthcare system and to people, even though vaccines were available. And so we needed to prepare for that spread. Similarly, in earlier waves with the pathogen. And so if those are our goals, what do we need to prioritize in designing the detection system? Well, the first thing that COVID showed us is that we need to prioritize geographic scale, because as if COVID did a lot of things as if it was trying to teach us lessons. I don't like the anthropomorphized viruses, but it does seem like it was trying to help us learn things. One thing it taught us is by having the first 4 major variants around the world all appear on different continents, it told us the importance of geographic scale for detecting new threats. We can also think about size as one of the important aspects of surveillance systems for detection. But there's rapid diminishing returns if your goal is to find a new pathogen early. And there's this famous rule of 3 that we mentioned in this paper on actually resistant surveillance right before the pandemic. But which gets published about every 10 years in a different journal with a different group of people. And the rule of 3 just says that if you want to be 95% sure of finding something of frequency below 1%, you need to sample 300 samples. If you want to see below 0.1%, you need to do 3,000 samples. If you want to see 1 over n with 95% confidence, you need to sample 3 over n. You need to sample 3n individuals. And so that means that if you're interested in seeing 1%, you really only need to do 300 cases. Maybe you want 0.1%, but the idea of sampling tens of thousands is probably overkill. And that's helpful because we can scale back and put the money elsewhere. What about the other kind of classic surveillance purpose of trying to quantify the burden of an infection? Well, there are a lot of reasons why we want to do this as well. We want to just be aware of trends so that we can make general planning assumptions. We want to know how much of the population might be immune from prior infection. We want to be able to evaluate whether our control measures work. So does the burden go down when we impose control measures? We want to be able to tell who is particularly affected and has maybe a geographic hotspot, as in this case in the United States, or race and ethnicity difference, as in this case where non-white ethnicities, non-white and non-Asian particularly, were disproportionately affected, especially early on in the pandemic. And related to that, identifying inequities. So that's something about the why. How should we do that? Well, in this case, unlike detection, where other things are important, here the issue of representativeness is absolutely paramount. The graph here is from Luxembourg, which was a country that sampled for many weeks of the pandemic, sampled something like 10% of its population every week. Doesn't have a very large population, so that's a feasible thing for a country like Luxembourg to do. But it was roughly speaking, a random subset, and it was a subset, and it gave them an ongoing picture so that they could, for example, look at these countermeasures and make an assessment of whether they were having a desired effect in nearly real time. Another value is that's important in quantifying the burden is data completeness, because if you want to know about equity, you need to know who's getting infected. You need to have all the fields filled out in the line list of whether people are possible. That has been an enormous problem in the United States. Something like 30%, I think, of COVID deaths had missing data on race and ethnicity, for example. And I may have that number wrong, may have been cases, but the enormous percentage were missing those data. And that, of course, makes it harder to use the data for public health decision making. By contrast, in the UK, which I'll get to in a minute, but just to digress for a second, in the UK, where the data were much more complete, an early question they had was that they were seeing also in their racial minorities a disproportionate impact of severe outcomes. And they asked a very simple question: is that because they're getting infected more, or because they're having worse outcomes when they get infected, or both? And they were able to trace it to an occupational set of occupational associations, and to higher, because they, as I will mention in a minute, had much more complete data. They were able to show that those groups were largely getting higher rates of infection, and that their outcomes were not much worse than the rest of the population once they got infected. And so the obvious intervention is to try to prevent infection rather than to focus on so there are very practical things you can do if you have representativeness and complete data you can't do if you have American style data, as we've had it in COVID. However, limited quality of data does stimulate innovation, and Michael Mina, who used to be here, and James Hay, and a bunch of us in 2021 came up with a notion that if you don't have good data that you believe on the trend in the course of infection, the data on the viral load can give you a clue even in the absence of multiple temporal slices. So classic way to figure out if the infection is going up or down is to sample it at multiple points and see if there are more people infected or fewer. But this approach uses a single cross-sectional slice and uses the fact that new infections, those that happen just recently, are going to have higher viral loads on average in COVID than infections that have been long-standing. And in a growing epidemic, as in a growing population, in a growing epidemic, most infections are new, just as in a growing population, most people are young. In a shrinking population, most people are old. In a shrinking epidemic, most infections are old. So using those two facts, you can use the distribution of viral loads to infer the direction of the epidemic, even without having to know them. So that's just an example of trying to be clever when you don't have the data calling you. But usually being clever is the last thing you can do. I'm clever and have good data, much better. And this was a point made by none other than your own Natalie Dean, very eloquently in this article in Nature, pointing out that the way to get representativeness is to use very straightforward random sampling of populations. And she gives all the arguments for why that's the clever thing to do, and a good thing to do, or not a clever thing to do. Clever is bad. Why it's the right thing to do, because then you don't have to be clever with the data. It tells you what you want to know without a lot of being tortured. And the two countries that did it that I'm aware of on a large scale are UK and Luxembourg. And the UK did it on a much larger scale. And this is a partial list of the things that they were able to figure out just from their random samples of the population, with linkage to health records, but many of them without doing that. And it's pretty amazing list. So infection prevalence and cumulative incidence, they were able to detect and see the growth rate of new variants. They were able to estimate vaccine effectiveness in various interesting permutations. They were able to look at the symptom profile and how it changed through time, because the different variants have different symptom profiles. They were able to see the infection and whether previous infection was protective. I mentioned equity measures and the infection fatality. That's a huge number of things to be able to figure out, and it comes from one very simple but very rarely implemented education. So that is the most valuable lesson of the pandemic, is that we need the capacity to be able to do these examples of the population, understand what's going on. In my CDC role and trying and have a lot of support for the idea, but not money support yet for the idea of trying to pilot this so that we can do it better the next time. So I'm hopeful, but it needs to get done. So in the pharmaceutical world, there's this idea of a target product profile that we say, if I want a vaccine against this infection, it should be preferably one dose and not two. It should be at least this % effective. It should be injectable, blah blah blah, or administered by some other route. And for each kind of vaccine, for each application of vaccine, we define this list of what's necessary and what's desirable. And so kind of what I'm arguing here is that for surveillance design, we need to do the same. We need to figure out what it is we're trying to answer, and then design the systems to have the qualities that we need. And that means that we can spend a lot of money doing one thing, so by saving the money, not focusing on the things that are necessary. And I will not drag you through this in the table, but just have it here as an illustration of sort of how one could use it. So I mentioned the idea that surveillance is clearly some of these things, and maybe I'm making a bit of a stretch to call surveillance others of these things. So in the pre-COVID era, I would have agreed with that. So if you had said to me, is virus sequence a surveillance aspect? I would have said maybe not, but it's really something you just find out and then you know it. Is severity a surveillance question? Probably not, because you do a study, you get the answer, and then it's the answer. Similarly for transmissibility, natural history, spelling, like for any kind of disease that's not changing too fast, these are fixed quantities. You do a research study, you have the answer, and then you do it again for one. Everyone agrees that the number of these things that are by nature changing every day, cases, hospitalizations, deaths, everybody agrees those are significant. But in COVID, every one of these things on the left was changing on a monthly, if not faster basis. And that's because the virus sequence was changing, and because the population was changing in its level of infectiveness, its level of infection immunity and vaccine immunity, both going up as more people got infected and vaccinated, and going down as more people had immunity. And so every one of these things became a surveillance question. Does this terminology matter? I think it does. I don't love to talk about terminology. It's not very interesting usually. But I think the terminology matters for two reasons. One is that public health surveillance is exempted from human subjects, broadly exempted from human subjects rules. Not always, but to a large degree. And so if you're doing public health surveillance, and you can make a good case that you are, you can do things faster and with fewer limitations. Obviously, you need to respect human subject principles, but some of the paperwork gets easier. The second reason is that we need to be able to design systems that can answer these questions over and over. If you think that severity is a question you're going to answer once, you set up a very complicated, very detailed, gold-plated research study, and you do it very well once. If you're going to have to answer it again in a month and again in 2 months, then you set up a system you can repeat and do well, but maybe with a little bit less detail each time, but in a way that's repeatable. So the conclusions are pretty much the things that I've been saying, that surveillance is multiple activities, not just one, and that we should design our systems in ways that answer the questions as precisely as possible. For the second part, and I leave some time for questions at the end, but I do want to talk a little bit about the question of how to connect models carefully to epidemiologic studies. And this is a paper, it's a preprint with Kaya Joshi, whose PhD thesis is part of, and Rebecca His lawyer. And the working title of this project was, quote, "We got the parameters from the literature," unquote, colon, "improving the parameters of the literature." So that seemed a little bit pretentious or obnoxious, or both as a title. So we chickened out of using that as our real title. But I think some people in this room will recognize, the modelers at least, will recognize the phenomenon of how do you figure out what vaccine effectiveness is, or the probability of hospitalization given infection. You send the graduate student to go read some papers and bring them a number. And they do that, and hopefully you get a number that's relevant, and you use it, and then that gets cited in a whole round of modeling papers many generations later as being true. And hopefully they got the right number, but maybe they didn't, and maybe there was no study that actually measured the right number, so they got the best they could. And we think probably one should be able to do better. So we're trying to bring some rigor to this idea, and doing that is, I think, a big project, and we tried to start that project. So if you think about an individual-based transmission, an individual-based model just has individual people in the computer. They interact through a set of rules. They have a set of characteristics that determine whether, when they're exposed to infection, they get infected, how bad it is for them, whether they progress to being hospitalized, and so forth. When we run one of these transmission models, and individual-based models, just easier to think about in this context, we need to put in probabilities and rates at which all of these things happen. So the question we tried to start looking at is, what are those numbers, and how do you get the correlation? This is a very wordy slide. But the idea is to make that a little bit more formal. Okay. You start an individual-based model, you have a collection of people, each of them has a vector, which we call L, of characteristics that either are fixed, like their residence for the period of time of the model, or they follow some natural force, like their age. May also include the comorbidities, which do change through time. We're going to ignore that for now. And then you can alter some things in the model, like whether the people get vaccinated or not, which we call A. And we set up the model, and at the start of the model, we set a few people to be infected. We let the model spread the infection, and the model tells you which people get infected when and what happens to them. So each person has this set of variables L, which they are set by nature, A that are set by intervention, and E that are or exposure that are set by the contagion process. Then you have a natural history. So for something that's like COVID, that natural history might be start with exposure and then lead to infection, symptoms, diagnosis, hospitalization, ICU, and death. You might not be able to reach all of those states from any other. Maybe some of them require that you get the prior state, and maybe some of them you can jump over, for example, you might be admitted directly to the ICU. But just in the simple context, you have these things that can happen to you. You get exposed, and then these other things can happen as a consequence of your exposure or not happen. And so what the individual-based model kind of needs is a probability if you start out being exposed and you have your covariates of A and L, the fixed one, the variable ones and the fixed ones. What is the probability that you end up having any path through this thing? So if you have 6 different things that can happen to you, there are 2 to the 6 paths through the thing. 0, 0, 0, 0, 1, blah, blah, blah. 2 to the 6 of those. But some of those aren't going to happen, like if you don't get infected, you're not going to die of the infection. So it's a little bit less than that. But in principle, there are 2 to the 6 paths through this. And what the individual-based model really needs as inputs is the probability of each of those 2 to the 6 paths. Hard to figure out those, right? 2 to the 6 is a big number. And we rarely have the ability to measure 64 different pathways in an epidemiologic study. So we have to do something. So we might want, so those would be the marginal probabilities of each of the full pathways. You might also be interested in the marginal probability of some specific outcome, hospitalization, given you have a certain A and L, and you get exposed to infection. And that is something, if you're just interested in one of the outcomes, like hospitalization, that's something that's sometimes measured in vaccine trials. For example, there were very many hospitalizations in the randomized trials for COVID vaccines. There were more in the observational mimics of randomized trials, but you can figure out if someone who's 70 years old and has 3 comorbidities, you have enough data and gets the vaccine versus doesn't, what is the chance that they get hospitalized? So that's in principle something we can measure. But even that is not actually really measuring the right thing, because that's conditioning. That's not conditioning on their exposure. That's conditioning on just being a person in the trial. So you're not actually following people from the point of exposure. You're hoping that some of them get exposed and using those people who get exposed, which are going to be balanced between the 2 groups, because you randomize them to make some sense of it. So actually, the thing you would want, if you were going to do a proper causal estimate of those quantities, would be a human challenge trial where you fix both vaccination and exposure. And in another part of my life, I've written a paper suggesting that might, in fact, be an ethical thing to do under certain circumstances, at least in very low risk strata of health. So in very unhealthy people, it might have been It might have been ethical, what would have been ethical if they volunteered to include them in a human challenge trial for vaccines, but you're actually not interested in those people for the vaccines, but they're not the ones who need it from those. You're interested in the people in the high risk strata, so it would not have been ethical and they would have been volunteered. So this is not a practical option. So what do? What we do is we make a randomized trial. We do an individually randomized trial or a cohort study where we assume that we don't know who's been exposed and who hasn't, but we assume because of randomization or because of good control for confounding in a cohort study, that whatever exposure has happened is going to be the same in the two arms of the trial. Those who do get the vaccine and those who don't get the vaccine. If we assume that the vaccine's effects are multiplicative, meaning that whatever my risk would have been if I didn't get the vaccine, it is the same amount lower on a multiplicative scale if I did get the vaccine, then we can use these studies to estimate what the ratio of probabilities in our individual based model is, because we're saying whatever your risk is given exposure, it will be multiplicatively less by the amount measured in the vaccine trial. That was a too quick explanation, but that's what we go into detail about in the paper. As an example, this was a study, an observational study in Israel that I was played a small part in, where for each of these outcomes of any COVID, of symptomatic COVID, and of more severe outcomes of death, you can measure the cumulative incidence in the two groups, and you can compare that and adjust for confounders in various ways. And the ratio of those two risks tells you that 1 minus that is the vaccine effectiveness, and that number can be directly taken and put into the individual risk model. But that's just one of the many outcomes. So you have a bunch of different indices to fill in. Another thing you can do if you can't balance two groups of people that have exactly the same exposure, you can say, I'm going to condition on exposure in the study that I designed. And that's known as a contact tracing study. So there were a few studies during COVID, a big one in the UK, a small one that we did in Israel, and several others that estimate the vaccine effectiveness among people who you know were exposed. So you take people who tell you that they were exposed to COVID, you look at their vaccine status. If you can adjust for confounding appropriately, then you actually know the effect among people who have been exposed using the same multiplication. And that's what we did with this study of vaccine effectiveness against the Beta variant, which was rare but common enough in Israel, mostly among travelers to South Africa, and that we could get a vaccine effectiveness. So we've been talking about marginal probabilities, but sometimes you want the conditional probability. You want to know the probability that someone progresses from, say, diagnosis to hospitalization. If you know all the other probabilities, you can build an individual-based model without these conditional probabilities. It's essentially like the 3 fates. You spin the person's fate at the moment they are entered into the population. You decide what you draw from a distribution and figure out what their fate will be when they become exposed. Problem is, if you have something like a limited vaccine and you don't know at the start of the simulation whether the person's going to be vaccinated or not, you don't want to calculate all those probabilities then, because you don't know whether you're going to have enough of the countermeasure for that person to get it. And so you don't want to assume what their status is going to be at that time. So you would like to know if you measure someone at this moment, what is their probability of progressing given specific values of variables. Several people have pointed out that these conditional probabilities are not well-defined causal quantities. So if you are someone who defines a causal quantity as something, as a quantity that corresponds to an imaginable intervention, what is the effect of an imaginable intervention you could do in a randomized trial? You can't force somebody to be, you can't force somebody to get to the stage of diagnosis and then compare those who assigned to say vaccine or no vaccine in their choice, in their probability of progressing. Because forcing someone to get to the stage of diagnosis means you have to not only expose them, but be sure somehow that they get infected and they get diagnosed. And there's no intervention that corresponds. So there is they're problematic in that way, and they're also problematic because they almost always suffer from selection bias. And I'm not going to go through this entire diagram, but when you get people at one stage post the exposure and condition on getting to that stage and whether they get to the next stage, variables that you don't measure are going to lead to bias in the estimate. And sometimes we've had to do that nonetheless, and the only thing to do really then is to do sensitivity analysis around it. So as an example of that, this was a study that you guys led with Kaiser Southern California and our center at CDC, where the question was about severity of if you get infected, so that's past the exposure, it's a conditional an infection, what is your chance of proceeding to hospitalization if you get Omicron versus Delta? So what we would have liked to do is estimate the causal effect of Omicron versus Delta on the risk of hospitalization with an infection. You can't do that really, because, for example, the people who get infected with Delta are going to be different from the people who get infected with Omicron. You don't observe, for example, how recently they were infected with something else. Or whether they have some mild immunocompromise that you don't know about or something like that. So it is not a strictly kosher thing to do, but nonetheless we did it, knowing that it was not fully causally justified, and found dramatic differences in the risk of progressing from diagnosis to hospitalization and even to death. Into ICU between Delta and Omicron, and no differences between the first two Omicron variants of BA1 and BA2. And so then, because reviewers and friends both pointed out that this could be because Omicron could infect people with a lot of immunity, and Delta can infect people not as well if they had that much immunity, or it was somewhat immune escaping, it was much less. But these are not the same people, and so you're making unfair comparisons. And so we did fairly extensive sensitivity analyses to try to understand how much of this difference could be explained by plausible differences in the amount of underlying immunity in the two different groups. In other words, is it plausible that the difference would have gone away had we started with a completely uninfected population? And what is truly intrinsic severity, rather than the severity of those people who actually have it. And the conclusion was that unless those differences were exceedingly dramatic, it probably wouldn't fully explain the difference in severity, although it could explain recently. So this is kind of a little bit of a teaser. This is the first time I've given this part of the talk. I hope it was somewhat comprehensible. I think I need to work on it, but the broad picture here is that we're trying to improve on we took the parameters from the literature excuse that we all do. I think we need more dialogue between people who do causal inference and study design and those who do transmission models, because we're consumers of each other's product, but we don't always understand the mechanisms by which that product is made. So modelers can help define what quantities we need, and causal inference folks can help to identify how to estimate them. The marginal probabilities of one thing happening in literature are probably the least problematic, though they're often hard to find. And for conditional probabilities that start after the infection has already happened, there's the risk of bias and not just statistical uncertainty. So we'll stop there, acknowledge some other people who both funded this work and helped think through many of the issues, as well as the co-authors that I mentioned. Yeah. Yes.
What about the contact between the marginal probability and the additional probability?
Sure. So the marginal, and I, as I say, this is the first time I've talked about this, and I think there were some steps that were relighting, so I apologize for that. Let me try again. Focus on the effect of vaccination. That's the interesting question. One thing you might be interested in is the vaccinated versus the unvaccinated person. What is their comparative risk of getting hospitalized from COVID? That would be a marginal. Another thing you could be interested in is among people who are diagnosed with COVID and if they're vaccinated versus unvaccinated, what is their risk of getting hospitalized? Those are different, of course, because the risk will be higher if you're diagnosed, but might not be, the ratio might not be the same. And the reasons why it might not be the same include that the people who get to the stage of being diagnosed are not, even if you started in a randomized trial, the people in a randomized trial in the vaccine arm who get diagnosed with COVID and the non-vaccine arm who get diagnosed with COVID no longer are balanced in their covariates because they've been through a filter that's different. It's affected by the covariates, which is, in other words, selection bias. So if you did that randomized trial, this number is no longer a pure description of conditional of the causal effect of what you're of the vaccine on anything because there's this selection bias happening. Another perspective on it is that there's no way to get someone. You can imagine the human challenge trial that I described, where you vaccinate half the people and unvaccinate the other half of people and challenge them all and then follow them forward. And then count the events downstream. That would be counting each of the downstream events would be legit and comparing between the two. It's very hard to imagine an intervention trial, even on a wildly unethical one, where you get someone to vaccinate half the people and vaccinate the other half of people, and then get everybody to the stage of being diagnosed. Because, like, what does that mean? It would be probably giving a bigger dose to the vaccinated people on average. You might have to do it again because some of them wouldn't get infected the first time. Like, it just is not a well-defined study. And if you believe in emulating randomized trials as almost the essence of doing the causal analysis, which I've become a believer in that church, a new convert, so I really believe it. I probably won't get jaded at some point, but I really believe that that is now true. I really now believe that that is true. Then that's just another way of saying the fact that you can't think of the intervention is just another way of saying that it's not a causal phenomenon. Yeah.
Okay, so. Measuring a pandemic. Don't have another pandemic to test it against, right? Like we like all the surveillance to work better, right? Both the models and like our surveillance tools, right? But doesn't that mean we need another pandemic to test on?
That's a more real question than you could even know, in the sense that, for the surveillance part, I think it's pretty straightforward, that there are some lessons about how to set things up that you can do in advance, and you don't need the pandemic to kind of need the pandemic to make sure you did it right. But the UK managed to do it right on the first one, and it's because they set it up really well to begin with the pandemic. They did not plan on this. So on the surveillance side, I think it's pretty straightforward. On the forecasting side, before we get to the full-blown modeling, but just on the forecasting side, one thing you need is data, is you need snapshots of the data at every point in time, because the data about today is different today than it will be tomorrow. And we learn more about today as reports come in. Like there are lags in public health data, and they're not always short. They're not even always constant. We did some analysis in New York City, time from case PCR positive to report, and the distribution of lags changed dramatically week by week. So even trying to model that process is a mess. But if you're going to have any hope of doing it, you need to know every day, what did I think the truth was? And then the next day, how did that change and how did it change and how did it change? I'm trying to think how to say this diplomatically. Not all of the places you would have expected to save daily snapshots for posterity, save them for posterity. So even training the models retrospectively, it's turning out to be more challenging. So, but in principle, that's also pretty straightforward problem if the next pandemic is like but there are ways to train better, to solve the old problem better and better and better using the old data and your evolving knowledge of it. For the modeling, like the transmission dynamic modeling, is the hardest case because there are many degrees of freedom, and then it can build different so so for that, I think there's a lot we can do to get ready by designing high quality software that is ready to go for and readily modifiable for when you find out that it's not programmed for the right infection, but for something that's a little different. So there's having professional grade software, which is going to CDC, CDC that I'm working with, is focused on is really important, because then you at least know that the thing you have works for the thing you're trying to study, and you know how to sort of set up procedures for fixing it, as opposed to like, where is it on GitHub? Which is the model, for very understandable reasons when you're mobilizing academics. It's not our job to be prepared for an emergency, it's a job to do research and really different optimizations. But I think having a center that is designing reproducible operational software and systems is really a good thing, and that's one of the things we're trying to do. And I do think that, like, between the 2009 flu and Pox and COVID, we've learned a lot of lessons, and they're not like just needing more investment. doing that too. And that's a hard one, which we need to really learn, but a lot of them are very actionable, like we really need to figure out how to combine data streams better. We really need to figure out how to operationalize our example. I think it's a really important lesson. Those aren't like total pie in the sky. It requires a change in our political system. It's like operational stuff that we need to do. It's not free, but it's not implausible to do. So I'm reasonably optimistic that we can make a lot of progress, but we will be surprised by it.
How do you immunize against the fact that after a pandemic, everybody wants to forget it?
It's really hard to immunize when you're like, when one is the prime example of wanting to forget. It's a good question. I mean, it happened very, very quickly with this one. And it happened with Ebola. Ebola immediately wanted to repurpose all the money that was been allocated. So the real problem, I don't have any better solution than anybody else. I mean, I am sort of, I don't mean to keep saying CFA is the answer to everything. It's not the answer to everything, but it is. Well, I'll start with CEPI, which is the Coalition for Epidemic Preparedness Innovations. Is an organization that got set up after Ebola in West Africa. There's a paper in the New Journal by the Wellcome Trust and Adele Mahmoud, late Adele Mahmoud of Merck and Princeton, and forgetting the third author, it may have been Michael Australian, saying we need an ability to get vaccines all the way to through phase 2 testing, so that when an emergency happens, we'll be able to test them tomorrow rather than waiting for doing all the preliminary work. And CEPI now exists, and it's existed for 6 or 7 years, and is putting money into doing exactly that for a whole suite of viruses. I think that was like a real triumph of rational scientific and policy thinking, really figuring out here's an unmet need, here's what we would need to do it. And I think we benefited from that work, both at CEPI and the NIH, two different groups that were putting money into mRNA platforms and MERS coronavirus, and before that, RSV, which has turned out to have some similar chemistry. And those efforts, I think, I mean, somebody should figure out how many months they saved, but between the NIH and CEPI's work, there were many months saved, I believe, on getting vaccines for this one. So I think that's a hopeful story, that we can sometimes learn lessons and put money in place for longer than a week and do good things. CFA is an example of something that sort of grew out of the pandemic, and if we have a national budget, we might be able to continue. And it I think is another example of like trying to put some modest resources into, but significant resources into solving part of the problem. So I think there are some positive stories, but we forget and move on and figure out other things to fight about. So. Yes.
I'm really interested in part 2. I'm still trying to wrap my head around it. So I guess I went through with this in front of the model, and I'm curious because they typically will stratify the model like each group of multi different division probability size. So I'm curious if you in this framework, are we also kind of thinking about age specific probabilities or other problems like the demographics, and if so, how do we kind of estimate those quantities?
Yeah, I mean, so this chart thought of it as whole one stratum by one age, sex, comorbidity, and vaccine stratum. So you're sort of both natural things and your female things. So it's a separate problem for each one of these, but that of course makes it a much even bigger problem. So if you have age, sex strata and two vaccine strata, you have 16 times this many possibilities. Typically, like an article of faith in the way we study vaccines is that vaccine effectiveness or vaccine efficacy, whichever you call it, is a multiplicative quantity. And so whatever your risk is in the unvaccinated strata, it's 1 minus v times that in the vaccinated stratum. There's no reason why that number should be the same in every stratum, but if you don't measure it, what do you do other than assume it's the same across stratum? So there's a lot of that kind of thing, which I think is also not ideal, but reflects data limitations. There's just a lot less to say about that. I think that's what's like the best we're going to do. But with some of these other things where you have a choice of exactly what to measure, if I was worth kind of like point it out. But I think your point is also it's just a thing to do about it. And I do suggest if you're willing to say that there is perhaps clearer on this today.